Hello everyone, this is Professor Jeff Wilkerson at Luther College, bringing you an introduction to Exercise 8, Kirchoff's Laws and Spectroscopy from the Astronomy Lab book, Astronomers as Observers and Experimenters, as published by Kendall Hunt. I'm trying to show you the cover of the book there. There's the book that we're working with. So this is an introduction to our spectroscopy lab in here, and what we'll do in this lab is you will look at a bunch of different light sources, whatever you have available to you, and look at those light sources with a spectrometer. This is the spectrometer that we like to use here from Project STAR, and it's a very good spectrometer to use. It's got the light comes in through here. You have a small slit right here. The diffraction grating that breaks the light into the component colors is down here on this end. And you can see some 35 millimeter film, old school film that's been exposed over here to show the wavelength or the energy of the photons of the light. So you'll see the spectrum projected against this film over here with this spectrometer. Very handy, very good Project STAR spectrometer to use in this lab and this exercise. So basically, we want to look at the spectrum and think about what the spectrum is telling us about the nature of the system that we're looking at. So there are three types of spectra as outlined in the lab activity, and as you might have talked about in whatever course that you're taking to do this exercise. There is a continuous spectrum, and a continuous spectrum has all of the colors there. Now, it may have different ranges. So your continuous spectrum is going to look something like this. It's going to look like all the colors are there. And the way we like to think about the spectrum is to think about it this way. That's what you're seeing in this spectrometer, is you're seeing a spectrum that looks like this. And it might be brighter here, so you could do a representation of that as brighter. If you have crayons or colored pencils, you could draw this spectrum like that. So there's the brighter part of the spectrum, and it's dimmer over here. And it may fade out. Some of these continuous spectra may end here or may extend further out this direction. So they have different ranges. So when you look at a system, when you look at something with your spectrometer in this exercise, the first thing that we'd like for you to do is just describe, what does that spectrum look like? Where is it brightest? Is it continuous? Is it emission line? Sometimes you'll see bright lines like that where you see these emission lines. Or is it absorption line, where you'll see this continuous spectrum, something like this, with lines that are missing, dark lines on top of there. So you can see the absorption lines on here. So that's the first thing you just do. You talk about it. You say it's an emission line spectrum, and most of the lines, there are lines that range from this wavelength to this wavelength. There's a whole bunch of lines, more lines than I can tell you about, and they're clustered in the red or the blue in this wavelength range. Or maybe there's only 3 or 4 lines, and I can tell you exactly where those lines are. There's 3 lines, and it's at this wavelength, and this wavelength, and this wavelength. Okay? So this is how you want to go about looking at your light source and saying what that is. So we have a table in here. If you look at the table here, table 8.1 in the exercise, there's a place that you can describe what is the light source, and then you can do the description of the spectrum we were just talking about right here. So you want to do the description of the spectrum here, and then what you want to do is a sketch of the spectrum. That's what I just drew right here. So you've got the first 3 tables, the first 3 columns of your table filled out right here. You've got the light source, the appearance of the spectrum in the spectrometer. What does it look like? Is it a line spectrum? Is it emission line, absorption line, whatever? And then a sketch of what the spectrum looks like. We got the tables continued on the next page, so there's plenty of room to do a lot of different light sources, whatever you have available. And then what the spectrum is an intensity as a function of wavelength. This is wavelength across here, and how bright it is the intensity. So this is your eye looking at the intensity as a function of wavelength. You can turn that into a graph easily enough, and that's what we'd like for you to do. In this next box out here, sketch a little graph that looks like this. Intensity as a function of wavelength. Here, it's going to be a bright spike, nothing, bright spike, nothing, bright spike. There's your emission line spectrum. Your continuous spectrum is going to have something that looks like all of the colors here. And it may be to your eye, if it's uniformly bright across this region, then you're probably just going to draw it as uniformly bright, and then it just fades to 0 on the ends. If it's brighter right there as we drew, it might be brighter up there, and then fade off that direction, okay? So you have to choose what you think this emission spectrum looks like as an intensity as a function of wavelength. So really what we're doing is we're practicing saying, okay, we may see a spectrum. When we look at spectra in a book or in a paper or something like that, we may see the spectrum as a graph. We may see the spectrum as an image like this. We may want to know the description of the spectrum. So we're practicing putting all of these things together. What does it look like? What would it be represented graphically? And how would I describe that spectrum to somebody so that I know how to get the information out of there? And so we're practicing all of this, and we just want to see if we can translate what we see to something like this, so that when we see something like this, we can translate it back here and then tell us what that means. As we likely know, these emission line spectra come from tenuous gases. So if you're looking at a gas cloud and you see this is what you get. So you would expect to see emission line spectra from gases. Dense objects give you continuous spectra. On the surface of the Earth here, where we are, we would see dense objects would be liquids and solids. So if we have a solid or a liquid, we would expect to see a continuous spectrum. And so that's what we would get here. If we look at our tenuous gas backlit by our dense object, we have the continuous background, and then we see these lines in absorption. We get these absorption lines right here. And so these absorption lines would show up and would be our the absorption lines that we see right there. So this is a tenuous gas observed backlit by, this is a tenuous gas that we're observing, but we have a dense object behind it. Now in space, a dense object might be the photosphere of a star, for example. So the photosphere of the star can produce a continuous spectrum, and then that light has to come to us through various, perhaps, tenuous gases, and it might get turned into this absorption line spectrum. So that's the kind of thing that you're going to look at here today. So to use the spectrometer, if you're using a spectrometer like this, hopefully you can look at the sun, and don't want to look directly at the sun with your spectrometer, but a great patch of sky, a bright patch of sky. If it's cloudy, it's actually a pretty good day to do this work because the clouds are bright and you can point this slit at the cloud. So to do that, what I typically would do would be to come over here to a source like this. I try to block the light. Often what you want to do is block some of the light coming through the film so that it's not washing out the spectrum. And then you can block that light and you can point the slit at whatever it is you're looking at, and you can move the spectrometer up and down until you get what you want. Now in this particular spectrometer, sometimes these diffraction gratings are glued down and sometimes they're not, and you might have to rotate it around. So if I'm looking at this overhead light, I can rotate it around until I see the spectral lines from the fluorescent light overhead. And in fact, so I've rotated the disc and I've got the lines lined up squarely in the film. On the left in the graphic region, there's a green line in the fluorescent lights, and that green line we can use as a calibration. There's a small tick on the bottom, just below 550 nanometers. There's a small tick that should line up with that green line. And we can either take a pencil or a pen and use that hole that's right there and adjust this back and forth to make it line up, but it moves pretty rapidly, so sometimes it's better just to say, I'm a few nanometers off, and I'm just going to subtract or add that few nanometers to my measurements over there. So we can do that with the fluorescent light. If we want to look at the sun outside, we don't look directly at the sun. We point at a bright patch of sky, and we try to block the light coming in over here so it doesn't wash out the spectrum. So that's what we're trying to do, is shield some of that light. Another source that would be very common in an exercise like this would be a gas discharge tube. Here we have a gas discharge tube. So we plug this thing in, and this will glow. And this is an actual neon tube. And so this will glow very red when we plug it in. And we want to look at the gas, the emission from the bright line that's right in here. And the way we want to do that is we want to make sure what we're doing is pointing at it with the slit, not with the film. So the slit needs to be pointed right at it like this. So ideally, we want to get pretty close to this thing. If we have this lamp, we want to get up right pretty close like that, so we make sure we're pointing the slit at the light and not the film. Not this, but this. Okay, and sometimes having a lab partner help you with that, get this aligned and pointed where you want to point this thing would be a good thing. So what you do is you have a lot of sources like this, or the sun, or the fluorescent light overhead. An incandescent bulb is a great light source. If you have an incandescent bulb, you can rotate the incandescent bulb, put it on a variac, and change the voltage. And if you change the voltage, variac's a variable power supply, and change the voltage across the filament, that's changing the current through the filament. It's changing the temperature of the filament. And as you change the temperature of the filament, the intensity changes of the light bulb, but also the color of the light bulb. And so you can watch this light bulb go from redder to bluer as it gets hotter, and you can look at the spectrum and say, what happens to the spectrum? Can you tell any difference in the spectrum? Is it brighter in one region of the spectrum at one voltage and brighter in another region? Can you not tell that? Does the wavelength range change? Do you see more wavelength at one voltage and less wavelength at another voltage? These are the kind of subtle things that you're looking for in this experiment. When I do the experiment with my students, we often will have some unknown gas tubes and some spectral identification charts, and to say, can we look at the bright prominent lines, the most prominent lines in the unknown tubes, and identify where those are, which element this is most likely to be from the spectral identification chart. We fill this out, and we look at all of these spectra, and we get an appreciation here for what we can do with spectra. Remember, emission line spectrum is going to be from a tenuous gas, continuous spectrum is going to be from a dense object, and a absorption line spectrum is going to be this dense object observed through the tenuous gas. So we get these absorption lines that appear in the exact same location, the exact same wavelength as the emission lines from the gas if they weren't backlit. That's pretty much what we got. Good luck with this exercise, everybody. I hope it goes well for you, and thank you.